When Google unveiled Willow in December 2024, it was not announced with fireworks, glitzy demos, or the kind of polished corporate spectacle the tech industry has grown accustomed to, but instead with an almost understated, scientific formality that belied the magnitude of what had just happened. Because Willow, unlike its predecessors, was not merely another incremental attempt at scaling quantum processes but the first publicly revealed system to pass a threshold so long theorized, so heavily debated, that many in the field had come to quietly wonder if it would ever truly be crossed. And that threshold was fault tolerance at scale, the elusive moment when adding more qubits no longer increases fragility and error but instead reinforces stability, where error correction stops being a leaky patchwork of compensations and begins to work as a self-strengthening architecture. And in Willow's case, this meant taking more than 1,000 noisy physical qubits and weaving them into a lattice that yielded over 100 stable logical qubits, error-corrected, reproducible, and scalable, a configuration that not only computed with speed but, more importantly, with trustworthiness, because in quantum computing speed without reliability is meaningless, and up until Willow, that reliability had remained the Achilles heel of the field, the reason quantum supremacy demonstrations, like Google's own Sycamore experiment in 2019, while impressive, remained essentially laboratory curiosities, incapable of scaling to real-world impact. But Willow changed that, and it changed it in a way that startled even seasoned researchers, because instead of the expected pattern where scaling worsens noise and instability, Willow exhibited exponential error suppression, meaning that as logical qubits increased, the rate of error dropped, a reversal so profound it represented a pivot in the very psychology of the field, because suddenly the dreaded wall of instability was no longer looming in the near distance. It had been breached, and the implications of that breach were staggering. Because once a machine can scale while improving accuracy, then the race to build larger, more powerful systems becomes not a distant hope but an immediate roadmap. And what those larger systems could achieve is nothing less than revolutionary. From simulating molecular interactions with such precision that entire drug discovery pipelines could be compressed from years to weeks, to modeling energy networks and climate systems with a fidelity classical supercomputers could never dream of, to breaking the cryptographic codes that form the backbone of global finance, defense, and private communications. And this last application was the one that sent shockwaves far beyond laboratories, because governments have been warning for decades about the coming of Q-Day, the moment when a sufficiently powerful fault-tolerant quantum machine could break RSA and elliptic curve encryption, the mathematical shield protecting everything from military secrets to online banking. And though Willow did not single-handedly achieve that, it pointed directly toward it, shrinking what had been considered a 30 to 50-year horizon down to a span that suddenly felt more like a decade, maybe even less. And when that realization dawned across agencies, corporations, and rival states, the enthusiasm that initially surrounded Willow's announcement was rapidly replaced by something else: silence. And in this field, silence is never accidental, because when Google had first achieved quantum supremacy with Sycamore, they had trumpeted the result loudly, triggering debates, critiques, and follow-ups across the scientific community. But with Willow, the script changed. The announcement came, headlines flared, whispers spread in universities and military circles, and then, abruptly, the updates stopped. The blog posts slowed, the research talks evaporated, and those who had been openly enthusiastic became guarded, evasive, even absent from the stage. And this was not the silence of failure, because when projects collapse, they leave traces, abandoned code repositories, leaked frustrations, critical papers dissecting why the promise fell short. But Willow left none of these, instead leaving a void that felt heavy, deliberate, strategic. The kind of silence that historically accompanies technologies deemed too sensitive to parade in public. And it is entirely consistent with how nations treat discoveries that brush against national security. Because when breakthroughs in nuclear physics, cryptographic algorithms, or satellite reconnaissance first emerged, they too were swiftly cloaked, studied under classified programs, and removed from the open discourse of science, and Willow, given what it represented, almost certainly triggered the same pattern. Because Google is not an isolated academic team publishing in a vacuum. It is a corporation deeply enmeshed with U.S. government research initiatives, from DARPA to the Department of Energy, and it would be naive to assume that a machine capable of accelerating the timeline to Q-Day did not prompt immediate consultations, evaluations, and perhaps restrictions, because no state can afford to let such power advance without oversight, especially when rivals, whether corporate or geopolitical, are racing in parallel, with IBM, Rigetti, IonQ, and Chinese state-backed teams all chasing the same goal. And in such a competitive field, revealing too much too soon risks not only losing strategic advantage but destabilizing the delicate balance of global technological competition. So the silence around Willow may well be the loudest confirmation of its success, a tacit signal that it worked too well, that it revealed too much, and that from here forward its progress would be tracked in corridors inaccessible to the public. And the most striking part of this entire saga is that Willow's breakthrough did not even come from a flashy demonstration but from what was supposed to be a routine benchmark, a random circuit sampling task used to test error rates, where Willow completed the assignment in under 5 minutes, a task that classical supercomputers, even the fastest today, would require a time span dwarfing the age of the universe to finish. And while that disparity was shocking, the deeper shock was in the error profile, the realization that scaling improved fidelity instead of degrading it, a reversal that confirmed decades of theoretical predictions about error thresholds but had rarely, if ever, been shown so cleanly. And from that moment, those inside the lab knew the ground had shifted. Because once reliability is achieved, once error correction becomes self-strengthening rather than self-defeating, then the ceiling on what quantum computing can achieve effectively disappears, and that understanding, that Willow had quietly moved quantum from the realm of promise to the edge of practice, was enough to alter strategies across industries and governments alike, which explains why after the initial ripple of headlines came a wall of silence. Because in technology, the louder the absence, the more sensitive the presence. And today Willow remains a mystery not because it failed but because it succeeded, because it represented a threshold too consequential to parade, a glimpse of a future in which the very architecture of our digital, scientific, and strategic lives will have to be rewritten, and if we are to read between the lines. When Google's Willow chip emerged in late 2024, it wasn't presented with the drama of a consumer launch or the polish of a polished keynote, but with a quiet, almost clinical release that only those paying attention could truly appreciate. And yet behind that muted presentation was a technological event that shifted the entire conversation about quantum computing from the speculative to the urgent. Because Willow was not just another quantum processor, it was a system that reversed the way uncertainty is handled, shaping a tool that didn't just guess patterns or approximate probabilities but reduced unpredictability to computable accuracy. And that realization changed everything. Because suddenly the question was no longer whether quantum machines could solve problems that classical systems could not, but whether we as a society were prepared for the consequences of a world where uncertainty itself becomes programmable, where the very limits of chance and complexity could be bent into frameworks of predictable resolution. And with that pivot, debates shifted from the purely technical, can we build this? Will it scale? Can errors be managed? To the profoundly political and ethical, are we ready to regulate this? Do we understand the societal risks? Do we have a public discourse mature enough to handle what happens when secure communication protocols, financial systems, and military infrastructures based on encryption can be broken not in decades but in hours? Because with Willow, the once theoretical threat became immediate, no longer a distant concern but a practical consideration, acknowledged quietly by executives, policymakers, and defense planners who understood that while Willow had not yet shattered encryption or rendered digital security obsolete, it had demonstrated the path, shown the feasibility, and collapsed the timelines from centuries or generations down to perhaps a decade or less. And that realization was seismic, because it reframed the entire roadmap of quantum development. suddenly pushing what had been considered milestones of the 2050s into the domain of the 2030s, if not sooner. And the response was telling, because while public statements slowed and press releases dwindled, inside labs and strategy rooms the pace of meetings accelerated, urgency replacing speculation. For Willow had not crashed, it had cleared a barrier, and when barriers of this scale fall, the air of discretion becomes heavier than the noise of celebration. And this is why Willow's achievement mattered so much. It did not deliver a consumer product or an enterprise service. It delivered a pivot, a recalibration of what timelines mean. And in doing so, it reframed not only industry projections but also institutional awareness, because what Willow proved with its measurable data was not magic, not myth, but the fact that with enough qubits and enough error correction, tasks previously considered unsolvable by any classical system could now be computed reliably. And that measurable fact spurred ripple effects across domains from medicine, where the simulation of drug compounds could be accelerated beyond the current bottlenecks of trial and error, to logistics, where global supply chains could be optimized in real time, to finance, where risk assessment and modeling could move into levels of complexity unreachable by traditional computation, to energy systems, where optimizations could fundamentally alter the efficiency of grids and materials. And yet as the potential spread outward, so too did the questions of governance. Because if Willow is a step toward that future, then understanding how to regulate access to such systems becomes as important as developing the systems themselves. And in that sense, Willow became less a machine and more a mirror reflecting back the unpreparedness of our institutions. Because researchers stressed again and again that Willow did not decode secrets, did not crack open the encryption vaults of banks and governments. But what it did was change belief, change perception, shift the possibility space from the speculative to the inevitable. And that recalibration carries enormous weight, because once the monopoly on knowing what comes next is broken, once the timeline is compressed into human lifespans rather than abstract centuries, the questions become about readiness, governance, and societal resilience. And this is why Willow is often compared to historical threshold technologies. The nuclear bomb, which forced humanity into an entirely new geopolitical reality the moment it proved functional. CRISPR, which redefined the ethical and biological frontiers of life, or artificial intelligence architectures, which altered how decisions, art, and labor are conceived, because threshold technologies are not about incremental upgrades. They are about rewiring what it means to act, to decide, to govern. And Willow entered that category the moment its test results proved that error, correction, and logical scaling were not speculative but demonstrable. Because in trillions of error cycles and logical reconstructions, Willow demonstrated a stability that turned what had been theoretical structures into engineering blueprints. And those blueprints do not vanish. They circulate. They evolve. They become the foundation for immense capacity. And that urgency is precisely why Willow triggered more discretion than fanfare, because its test, routine by design, intended only as a benchmark, produced results that reframed the entire field, taking what was ordinary and revealing it as extraordinary. A turning point where routine became revolution, where predictability itself became programmable, and from that point the silence grew heavier. Because when breakthroughs of this kind surface, they do not get abandoned. They get contained, studied behind doors inaccessible to the public, monitored by those who understand the stakes. And Willow's uniqueness lay in the fact that, unlike narrow tools designed for specific domains, it was architected for interconnected complexity, able to interpret layered systems spanning from climate modeling to encryption, from chemical pathways to defense logistics, which meant it was not bound to a single use case but to an entire spectrum of them. And that lack of scope, that breadth of potential, made regulation nearly impossible to define, which is why oversight shifted upward, from laboratories to ethical review boards, government agencies, and military intelligence units. Because even if Willow itself was still a limited prototype, the existence of a functioning threshold technology altered the hierarchy of capability, placing into the hands of its creators a system that could see, compute, and solve in dimensions beyond what human teams could coordinate. And that is precisely why its story ended not in public expansion but in silence. Because silence in these domains is rarely about failure. It is about containment, about buying time to decide how much the world is ready to know. And so Willow may now be evolving under different names, hidden within projects we cannot yet identify as quantum-powered, or it may be locked away until governance frameworks catch up. But either way, its meaning is clear. It is not about faster answers. It is about questions humanity has not yet asked and answers we may not be ready to face. Because what Willow truly represents is not a product or a processor but a pivot point, a redefinition of computation itself. And with that redefinition comes a responsibility we are only beginning to grasp.